Today I want to talk about the division theorem as it relates to the ring of real polynomials over R. In fact, you've already met the division theorem twice in earlier courses. Here it is for whole numbers, which you met in your course on number theory. I'll pause while you read it. And here's the variation for integers that you met in the course, relations, mappings, and equations over fields. Again, I'll pause to let you study it. To remind ourselves, let's review how we might use long division to find the quotient and remainder when, for example, 826 is divided by 3. We'd begin by dividing 3 into 8. So that's 2 times 3 is 6. 8 minus 6 is 2. We then bring down the next digit, 2. 3's into 22 go 7. 7 times 3 is 21. 22 take away 21 is 1. Bring down the 6. 3's into 16 goes 5. 3 times 5 is 15. 16 take away 15 is 1. We conclude that 826 divided by 3 is 275 remainder 1. That is, the dividend 826 equals the divisor, 3, times the quotient, 275, plus a remainder of 1. By the way, notice that the remainder, 1, is less than the divisor. Your experience with long division tells you that this is always the case. And the existence of such a remainder is guaranteed by the whole number division theorem. I mention this because you're about to see a similar condition in the division theorem for real polynomials. So, turning our attention to the division theorem as it relates to the ring of real polynomial functions. The theorem is as follows. Suppose p and f are real polynomial functions, and the degree of f is at least 1. I'm treating p as the dividend and f as the divisor. In other words, we're looking at dividing p by f. Then there exist quotient and remainder polynomials q and r, respectively, such that the dividend p is equal to f times the quotient q plus the remainder r. And either the remainder r has no degree, or its degree is less than the degree of the divisor, f.
What does no degree mean again?
It's the constant zero polynomial.
So instead of the remainder being less than the divisor, its degree is less than the divisor's.
Exactly. And once I show you how to do long division with polynomials, you'll see why this makes sense.
Why would we want to do long division with polynomials?
I think it sounds pretty cool.
By the way, knock knock.
Who's there?
Poly.
Polly who?
Polynomial. Why the third degree?
I don't get it.
Third degree means to interrogate someone.
In that case, that is quite a funny joke.
No, it's a stupid joke.
In fact, long division of polynomials is quite straightforward, as long as you remember how to do long division with whole numbers. For example, suppose p and f are real polynomials given by these expressions. We take p to be the dividend, so 5x to the power 4 minus 12x squared plus x minus 17 is to be divided by f, the divisor, given by 2x squared minus 3x plus 4. We proceed as though we are doing a regular long division.
You added a 0x cubed to the dividend.
You mean this term? I added it because I'm going to arrange that the various powers of x line up vertically, just as the units, tens, hundreds columns line up vertically in regular long division. Let's begin. We start by dividing the first term of the dividend by the first term of the divisor, That is 5x to the power 4 divided by 2x squared.
So that's 5 over 2 times x squared?
Correct. We write the result of this calculation as the first term of the quotient. The next step is to multiply the quotient term we've just calculated by the divisor. 5 halves x squared times 2x squared is 5x to the power 4. Five halves x squared times negative 3x is negative 15 over 2x cubed. And 5 halves x squared times 4 is 10x squared. Next, as in regular long division, we do a subtraction. Again, by analogy with regular long division, we bring down the next column, x. Notice that the new remainder has degree greater than the degree of the divisor. This, together with the fact that there is still a column that we have not yet dealt with, containing the constant negative 17, is a signal that we still have work to do. The process now repeats. We divide the first term of the new remainder by the first term of the divisor. Giving us the next term in the quotient, 15 over 4x. Again, multiply the new term by each of the terms in the divisor. Now the subtraction. Now bring down the next column from the dividend. And round we go again. Divide the first term of the new remainder by the first term of the divisor. Giving us the next term in the quotient, negative 43 over 8. Multiply this new term by each of the terms in the divisor. Now the subtraction. Notice now that there are no more terms in the dividend to drop down, and the degree of the remainder, namely 1, is less than the degree of the divisor, namely 2. Therefore, our calculation is complete, and we conclude that the dividend is equal to the divisor times the quotient plus the remainder.